It is my great pleasure to start the first day of the fifth workshop on algebra and graph theory and its applications. And for this time, what we have? Well, we have 5 working days devoting to the following topics. So the first one is theory of how regular graphs, such as strong irregular graphs, distance regular graphs, distance transitive graphs, Desert graphs, Neumayer graphs, and so on. And the next topic is theory of association schemes and coherent configurations. And during this workshop, we also will pay attention to some aspects of topological graph theory. Actually, it is the first time for us to pay attention to this branch of graph theory. And I'm really happy to introduce our first speaker, who is Istvan Kovacs, and he will give a talk on a class of edge-transitive bicirculants. Istvan is our regular participants and our good friend, so I'm really happy that you start the first day of the fifth workshop. The floor is yours.
Thank you very much, Rana, and good morning or good day, anybody. Thank you for the introduction, and I would like to also thank for the invitation. It's always an honor to have a talk in this nice conference. So this is a joint work with my colleague János Ruf from Hungary, from the University of Pécs. And today I will just a moment. Probably you don't see my slides yet, right?
Yeah, we cannot see your slide.
Yes, yes, just a moment.
You can try to share it, yeah.
Yes.
Yeah, now everything is fine. Mm-hmm.
Okay, sorry. So this is a class of graphs which actually was defined by capturing 2 simple properties of the Petersen graph. The Petersen graph clearly admits an automorphism with 2 orbits of the same size. Just a rotation does that. And if you look at the subgraphs induced by these orbits, only these orbits, you will get 2 cycles. So the family I'm interested in is the following. So it contains regular graphs. The valency is at least 3. And the graph gamma admits an automorphism with 2 orbits of the same size in one hand. The other condition that one of the subgraphs induced by these orbits is a cycle. And by this, I little bit relaxed the previous property. I'm happy if only one subgraph is a cycle. And in fact, this class of graphs with small valency have been studied before by different people and also under different names. And recently in this paper, which you see, the authors initiated the study of the edge-transitive graphs in this class when the valency is larger than 5. So let's see what are the previous results for small valencies. If the graph is trivalent, then it is called generalized Petersen graphs. And these graphs were introduced by Mark Watkins more than 50 years ago. And he introduced them with 2 parameters and then used the notation GP of NR. The first parameter, N, just the size of the orbits of the distinct automorphism. So the graph has 2 N vertices, and in each orbit, you can label the vertices with elements from Zn in such a way that the mapping an element to the sum I plus 1 becomes an automorphism, and also the vertices with the same label are joined by an edge. So I distinguish between orbits by colors. So we have the blue and the red vertices representing the 2 orbits. And because of the condition, I put a full cycle in one orbit. This is the red vertices. And also I can see this complete matching between the red and blue vertices, and still remain to write the edges between the red vertices. And this is given by the next parameter. So the next parameter R, you can define it as the label of a red vertex joined to the red 0. So in the picture, this is 2 or 3. And this completely defines the graph, which is a Petersen graph. And we now obtain with this representation the Petersen graph as GP of 5,2 or GP of 5,3. Frucht, Graver, and Watkins also proved that the generalized Petersen graphs, there are only 7 H-transitive them, and these are the 7 graphs. All of them has a name and all of them appeared in different contexts as well, except the last one, which, as far as I know, it is no name, but only 7. The point is that there are only 7 H-transitive. So basically, we're interested in the H-transitive graphs in this class. And the next case, the tetravalent graphs. The tetravalent graphs are called rose window graphs, which were introduced by Steve Wilson much later. And for rose window graphs, we need 3 parameters. We still have n and r, and n is the number of vertices divided by 2. And we can still use the same labeling as before. And the parameter r defines the edges between the red vertices, just as before. And we need an extra parameter a, because between the blue and red vertices, we have 2 complete matchings. So if you fix the blue 0 vertex, it is always connected to the red 0 by default, but it has one more neighbor, and this more neighbor is given by the parameter a. So in the picture, you get the graph, the rose window graph with 16 vertices and parameter 2 and 1. And in the same time, this is a famous graph. This is the so-called Vries graph. This is a lexicographical product with 2 independent vertices with the full cycle. And this graph is also like the Petersen graph. This is also an H-transitive graph. The classification of H-transitive graphs, rose window graphs, was given by Claudia Kutner, Dragan Marušić, and myself in 2011. And in that case, we have infinite families. In fact, we divided the graphs into 4 infinite families. So this is a little bit different. This is much different from for the 3-valent case. For the 5-valent case, the graphs are called Tabachian graphs, and these graphs were introduced 2015 by Arroyo and her co-authors. I will show the co-authors in the next slide, so you will see all of them. And they use the notation T for the graphs. And now you have one more parameter, and I don't want to explain much about the parameters because it's very similar like before, but just would like to give the example, the icosahedron graph. And you can see that the icosahedron graph also appears as a Tabachian graph. It has an automorphism order 6, 2 orbits, the red and the blue. And in the blue orbits, the induced graph is a cycle. It turns out that for the 5-valent case, in this class, there are only finite number of H-transitive graphs. The icosahedral graph and 2 more small graphs, the complete graph on 6 vertices, the complete bitetrator graph on 12 vertices, K66 minus the complete matching. And that was proved by these people, Arroyo, Isabella Hubbard, Claudia Kutner, Eugen O'Reilly, and Primož Pál in the same paper. Now we arrived the last family, which was introduced recently by Robert and his co-authors. These are the hexavalent graphs in the family, and they call them Ness graphs. And now you need one more parameter, and I don't want to go through the details with this presentation, but this is the famous lattice graph, or this is the usual strong regular graph lattice graph, which has vertices the 4 times 4th grid. And in order to show that this is really an S graph, we just take the automorphism defined below. So that means you take a translation any vector in the vertical line, 1-step translation, followed by a reflection along the diagonal. So if you start with the blue 0, you have to go up 1 and reflect. You will get the blue 1. You go up and after reflection it stays at 2, and so on. You will get the zigzag, and it turns out that the blue orbits, the induced subgraph is a cycle in that case as well. And this shows you that this is really an S graph. This graph is also H-transitive. So far, all examples we had, I showed you the H-transitive examples. And now you have the question, what are the H-transitive Ness graphs? And again, here in that case, like in the 4-valent case, we have infinite families. And they managed to classify them under the further restriction that the graph contains triangles. The girth is 3. And in that case, the first family contains just sporadic 6 graphs, and to have 2 infinite families in B and C. So in the same paper, they also carried out an exhaustive computer search for H-transitive graphs in the class C, which have either valency 6 and order at most 220, or the valency a little bit larger, between 7 and 10, but the order is at most 100. And they found 66 hexavalent graphs and none of valency larger than 6. And because they posed 2 questions in the paper. The first question was, for which number D larger than 6, the class contains at least 1 H-transitive graph of valency D, and for which D does the class C contain infinite many H-transitive graphs of valency D. It turns out that among the 66 H-transitive hexavalent graphs, there's only one which has order twice an odd number, and this is the complement of the Peterson graph. And this motivated our research with János Ruf, and we consider the H-transitive graphs in C whose order is twice an odd number, which is quite a restriction, but on the other hand, we put no restriction on the valency, and this is the result which we get. So the class C contains the following H-transitive graphs of twice odd order, and this is just a complete graph on 6 vertices, the Peterson graph in its complement, and the V's graphs. So in the next, I would like to show you some ideas how to prove this result. And the first step is in our proof was to consider the graphs with a primitive group. And our tool to do this is the following classification result due to Peter-Müller. Peter-Müller classified permutation groups of degree 2n, which contains an element with 2 orbits of the same size. And this is exactly which our graph has, this property. So it turns out that there are 2 possibilities for a primitive group. The primitive group either belongs to an affine action, and the group is an affine permutation group with very small degree. The degree is either 4, 8, or 16. Or the group is an almost simple, the action has an almost simple action, and the group is an almost simple group which belongs to one of these 6 families. I don't want to read through all the families, but just point out that the good thing for us is that in the almost simple case, all the permutation groups which are obtained are double transitive, except in family B. And family B, when the action is, when you have the action of the A5 or S5 under 2 subsets. And you can guess that this is the case which belongs to the Peterson graph or its complement. And this is the color red which you get. So if G is a GH transitive graph in the class C, such that G is a primitive on the vertex set, then the graph is isomorphic to one of the following graphs, either the complete graph of order 6 or the lattice graph. The lattice graph belongs to an affine action, the Peterson graph or its complement. So if you want to study this problem, we can assume that right at the beginning, if the graph has a group acting transitively on the edges and the vertices, we say that the graph is GH transitive and GF transitive, and we can assume right at the beginning that there is a block of implemmentivity for this action, a non-trivial block of implemmentivity, or shortly, I will just say a block. And in the next slides, we study blocks, and we also study the corresponding quotient graphs. So this analysis was the crucial part of the proof. So first of all, I would like to define what I mean by a quotient graph. So this is a general definition. Take any graph, take any partition of the vertex set. And if you have a vertex V, then I will denote by pi of V the class from the partition which contains the vertex. Then the quotient graph is defined to be the graph which has vertex set, the partition, and the ages are given by those classes which contains adjacent vertices and are different. Basically, this is the meaning. So just some small refinement of this definition. I say that the gamma is an R cover of the quotient. If it is also true that for any age, the partitions are different, that means I look at quotients when the partitions, then the classes doesn't contain entirely ages. This is one condition. And the other condition, if you look at a vertex and look at its neighborhood with another class, then the intersection is, if it's non-empty, it's always a constant number. So any vertex has a constant number of neighbors in another class. In that case, we say that the graph gamma is an R cover of the quotient graph. Plus one more terminology. If it's an addition, it happens that, which for us it will happen often, that the partition is an orbit of some normal subgroup, then we say that it is a normal R cover. And in that case, we also write, instead of gamma divided by pi, so sorry, this would be pi, gamma divided by pi, we will write gamma over n for the quotient graph. Okay, let's recall one important property, some important properties of these quotient graphs. So we say that a block system B for a transitive group is normal if B is formed by the orbits of some normal subgroup. And then suppose that gamma is a connected G vertex and GH transitive graphs. And suppose that B is a normal big block system for G and denote by K the kernel of the action of G on B. Then it follows, you can form the quotient graph, and it follows that the original graph becomes a normal R cover of the quotient, where R, you can find R easily, just fix any vertex and any block, and you just look at the number of neighbors of this vertex in this block, provided that the block intersects in the neighborhood. And this is the first thing. And if it happens that it also happens that this R is 1, then it follows that in this case, the quotient graph and gamma have the same valency, and the kernel acts regularly on any block, and the quotient is also vertex and H transitive graphs, and this group G over K, actually the image of the action becomes X vertex S transitively on the vertex on the quotient and also transitively on the vertex on the edges. And this procedure will be very useful for us. So now let's go back to our graphs. Let's go back to our problem. And I will give you 4 lemmas about blocks. And for these lemmas, I would like to set the following notation. So from now on, gamma is a GH transitive graph in this class C. The order is 2 times n, and the valency is at least 6. I fix the notation C for the cyclic semi-regular subgroup with 2 orbits. And also one of the subgraphs induced by these orbits must be a cycle. And I also fix the notation B for a block for G, and let this calligraphy B denote the block system induced by B. Now, there are 2 options. If you look at a block, the block, it may be contained in one of the 2 C orbits. So C has 2 orbits, B may be contained in one of them. And in that case, we say that the block is cyclic. And we will study first the cyclic blocks, and we will study after that the non-cyclic blocks. And for the cyclic blocks, we have the following lemma. Suppose that the block is cyclic, and also suppose that the size of the block is non-trivial, first of all, and also the size is less than half of the order of C. Remember, later we study the odd case, and this will be guaranteed automatically. it's easy to show that the block cannot be the same size as C. So in that case, it turns out that gamma is a normal one cover of the quotient, and the kernel of the action is nothing else but the stepwise stabilizer of the block contained in the cyclic group C. The second part says that, moreover, this quotient graph still belongs to the family. And this is a kind of important message, because under such condition, we have a graph in the family, we can always reuse it to a smaller one. And this allows, for example, inductional proof and etc. And the proof is, the first part is it's obvious. So it's clear that in that case, because the blocks are contained in this orbits of C, and C is regular on both orbits, it's easy to see that the blocks are nothing else but the orbits of the stabilizer of B in C. And this immediately tells you that this is a normal block system. And we just have this basic proposition: if a normal block system, then the graph should be a normal R cover. And now we just have to find this R. And to find this R, we use the fact that if you pick a vertex V in an orbit, C orbit, such that the subgraphs induced by this orbit is the full cycle. So you are just in this orbit, and V is contained in this full cycle, and no other vertices, it has only two neighbors inside the orbit. And because the size of B is less than half of C, you can see that the neighborhood of this vertex V has exactly one common vertex with a block intersecting V. And this shows you that R must be 1, and this is an R cover. And if this is an R cover, then the kernel must be regular in one hand, but on the other hand, the kernel contains the stabilizer of B and C, and that means the kernel and the stabilizer must be the same. So this is how you get the first part. And the second part is, you just have to observe that this induced cycle on the C orbit will project to an induced cycle of the quotient graph, and this tells that the graph is still in the family. Okay, in the second lemma is even shorter. Then we now turn to non-cyclic blocks. Suppose that you have B as a non-cyclic blocks. Then, first of all, now a block intersects both orbits of C, and it turns out actually the block is a union of two orbits of the stepwise stabilizer, and C acts transitively on this induced block system, and the kernel is equal to the stepwise stabilizer. And the second part says that if this non-cyclic block has size larger than 2, then, and B is also minimal, then the block system is normal. And really a sketchy proof. So the first part, I suppose, is not difficult to prove. And the second part, I will just observe the trick which we use many times later, that if you have a non-cyclic block and it's minimal, then the stepwise stabilizer of the block induces a primitive permutation group on the block in one hand. But in the other hand, because the block is non-cyclic, it follows that this primitive permutation group contains a semi-regular cyclic subgroup with two orbits. And this just comes from the stepwise stabilizer of B and C. And because of that, this group is just described by Muller theorem, and you can use this Muller theorem to analyze this group and its properties to get further constraints on the graph. Okay, let's go to the next lemma. I promised 4 lemma, and in the last 2 lemma, now we need the condition that n is odd. And finally, our goal is to show that if n is larger than 5, then there is always non-trivial cyclic blocks. So remember, so we have these graphs in this family C, and whenever we have a non-cyclic block, in the odd case, it reduces to a smaller graph. So we always have this process, and this will be basically our strategy later. As we started with so we know that one graph is in the family, the complement of the Cartesian graph. And what we do, we just started the next one in the family, which projects to this one. And we would like to show that this doesn't exist. So this is the existence of non-trivial cyclic blocks is a crucial step. And we will prove this in two lemmas. In the first lemma, which you can see, we exclude the case that B cannot be of size 2. And this is, in my opinion, this is quite interesting proof. And here I would like to show you some more details because I use some results about Cayley graphs of cyclic groups. So let's prove it by contradiction. So suppose that it's not true and take a block of size 2. So this is a block which contains two vertices, U and V. So further assume that the subgraph induced by the orbit containing U is the full cycle, is a cycle, and pick an element in C such that UC is an H. Of course, such element C should generate the whole cyclic group. Now define the following involution. So T is an involution which just switches the vertices inside the block. And because this is a block system, it turns out that this T is not an automorphism of your graph. We don't know that. But what we know is that any element in G commutes with this T. So the group generated by G and T is just a direct product. And now we introduce a new graph. The new graph, gamma prime, has the same vertex set as gamma, but the edges we take to be the orbit of this fixed edge UC under this new group G times the group generated by T. Now we have a new graph, and you can observe that on this new graph, this G times T acts. And this group contains a regular and cyclic subgroup. Namely, the group generated by C and T is regular, and it's also cyclic because the order of C is odd. And because of that, this new graph becomes a Cayley graph over H for some subset R, which we don't know yet. By definition, this new Cayley graph is R-transitive because just we defined its H set as an orbit, and any H-transitive circulant is necessarily R-transitive. So we get an R-transitive circulant, and we would like to show that this is impossible. This such gamma prime cannot be R-transitive. And here is the point which we need this result. So this is a classification of R-transitive Cayley graphs over cyclic groups. And this is, I wrote a paper about it, and independently Tsai and Lee wrote a paper about it, and the papers appeared in the same time, the same year, different issues by the same journal. But in fact, I have to admit that this result is just a consequence and not so complicated to derive from deep structured theorems about Schurings over cyclic groups, which was done before us by Sergei Yevdokimov and Ilya Ponomarenko. So now I will divide the R-transitive circulants, R-transitive Cayley graphs over cyclic groups into 4 families. The first 2 families is defined algebraically. The last 2 families are defined in terms of the connection set. So suppose you have the Cayley graph over cyclic group H with connection set X. It is either complete, and no need to explain that, or it's a normal Cayley graph, which only means, I just recall the definition, it only means that if you take the group of right multiplications, this is normal subgroup in the full automorphism. And we will use this later, this property. Now, in family C and family D, the graph are described in VRD connection set. In family C, there is a subgroup, a proper subgroup D of the subgroup H, such that X is a union of D cosets. And this is the important information which we have to remember. And it's also true that if you construct this corresponding Cayley graph, is still connected and R-transitive, but this is not important to us. And the last family is very similar, but in that case, you need 2 subgroups of H, D and E, such that H can be written as a direct product to D and E, so that D and D have co-prime orders. And in that case, the connection set is not the union of cosets, but it is a product of D dash times Y. The D dash is just all the group elements in D minus the identity, and Y is just subset of the other subgroup E. And also you have some condition on the corresponding Cayley graph, but it's not important. Okay, we would like to apply this theorem, and we would like to, for that purpose, we have to find R, if we would like to apply it. And remember, we have this circulant gamma, which we started with two special vertices U and V, and the cyclic subgroup, and the orbits containing U and orbits containing V. The orbits containing U is a full cycle. The orbits containing V is just union of cycles. It's not necessarily a full cycle, it's union of cycles. So you can fix, you have a unique number K such that in the other orbit, V and VCK is an edge. Now, it's known that how to find a connection set. If you know the regular subgroup, the connection set contains all group elements of H, which maps U to a neighbor. Now, the H set of this new graph is a union, is just an H orbit of this direct product group, but in fact, this H set is split into two G orbits. The G orbit of the HU-UC and the G orbit of the VVC. Now, if this V and VC would be an edge in gamma, then actually the H set of gamma prime would be the same as the H set of gamma. But what does it mean that V and VC is an edge of gamma? It exactly means that this K is 1. So if K is 1, then actually gamma prime, the graph gamma prime is the same as gamma. And because of that, we have this condition. If K is not 1, then these are two different H orbits of G. And moreover, this T swaps this H orbits. So any neighbor of U in gamma prime is either also a neighbor of U, or T maps this neighbor to a neighbor of V. And that's why we get this description of the neighborhood in the case when K is not 1. And if you introduce the set S, which contains all elements from C, such that V of C is a neighbor of U, then you can prove that two things can happen. This is either inverse closed if K is 1, or it's disjoint with its inverse if K is not 1. And then you find the connection set R in the form S prime union S2 prime, when S prime contains 4 elements from the subgroup C, and S2 prime contains these elements from its coset. So remember, now our H, the cyclic group H, is generated by C and generated by T. And C is an element of order N, and T is an involution. Okay, so we have this description. We found the connection set, and we would like to find that is it R transitive or not. And we just have to look at the families, and we consider all families case by case. So is it compact or not? And this is clearly impossible. You can see it because the graph gamma prime has even order, definitely. This is a bicirculant. And also the valency is even. The valency is the sum of this cardinal, the cardinality of this set plus the cardinalities of this set. If K is 1, we have 2 elements here, and K is 1, then S and S inverse closed, and actually we have one set S here. But this set, because it's inverse closed, it should be, any element should come with pairs. And because N is odd, this is a set has even size, and this has size 2. So the cardinality is even. If K is not 1, we have 4 elements here, and we have 2 times the cardinality of ST, which is also even. So the valency is always even. The order is even, is not compact. But so this is not a compact graph. And the next family is the graph is normal. Normal means that the group of right multiplications is a normal subgroup in the automorphism of the graph. But this implies that the stabilizer of this automorphism group contains group automorphisms, and this group and the stabilizer, because our transitivity is transitive on the connection set. So we have the connection set basically is an orbit of some subgroup of the automorphism group of H. But that would mean that any element in the connection set has the same order. But clearly, this element C has order N, which is odd, and any element here is of even orders. So the scaling graph cannot be normal. I will just explain the family C and I will skip the family D. The family C, the condition that the connection set, which is here, is a union of some D cosets for some subgroup, non-trivial proper subgroup D. Now, if two cases, you have to consider if D is odd, that means D would be a subgroup of C, and that would mean that this part is a union of D cosets, but this part has 2 or 4 elements. This clearly is not possible. And if D is even, then it contains the involution, but that means multiplying R with this involution should preserve R, and that would mean that T times H prime is H2 prime and T times H2 prime is H prime. So these two sets have the same cardinality, and you can see that it's either 2, but in that case, the cardinality is S, which is larger than 4. And this is the point when we use that the valency of the graph is at least 6. So this is the point that you need to prove that you use the fact you need to use the condition that you are considering graphs of valency at least 6. And if K is 1, this happens if K is 1. If K is not 1, then this cardinality is 4, and this cardinality is at least 8. It's also not possible. So I will skip the details. It's a very similar argument, but I think it's enough from this proof. So we are ready to accomplish our goal, which was to prove that there is always a non-trivial cyclic block, and I will just sketch the idea. I will not go to the details here. So what we did, we construct a cyclic block. And how to do it? We take a minimal block, we take a fixed vertex in this block, and suppose that K is a kernel of the action of G on this block. Now, by the previous lemma, we may assume that B is non-cyclic, and because of the lemma, we can also assume that B has larger than 2. But if B is larger than 2, then we can use Muller theorem and to describe the kernel actually. And it turns out it's possible to show that for any block in the block system, it contains a unique vertex U prime such that the stabilizer of U in K is the same as the stabilizer of U prime in K. So for any block, you have this distinguished vertex. And it turns out that these vertices U form a block, and the block has size exactly the same as B because of the previous condition. But on the other hand, it's clear that the size of the block is odd because the block system is non-cyclic as n is odd. So what you found a block of odd size, but a block of odd size must be definitely a cyclic block. So you obtain your cyclic block. Okay, so we have one more. So that was one crucial step, was to prove that we have a cyclic block for the group acting H transitive on the graph. And the other crucial, to finish the proof, we just used one more lemma. And for that lemma, I would like to keep the notation, as we said before. And the lemma meaning is that suppose that you somehow know the group of the graph, and you also know one stabilizer of one vertex stabilizer. And this lemma gives then some conditions that the group should satisfy. And we will see that in some cases we can construct the group without knowing the graph. We will see that is possible. And the lemma simply says that in that case, the group should contain an element of order and satisfy this condition. I will not prove this, but just really show you the idea. And the idea is you represent your graph as a coset graph. And in the coset graph, you take the stabilizer of the vertex U such that the orbit containing this U is the full cycle. I mean, the C orbit is a full cycle. And you also choose the element C from the cyclic group so that U and UC is an edge. So under such condition, your graph is isomorphic to this coset graph, and then you can show the condition satisfied for taking H to this stabilizer and taking G to this element C. So C is order n. and this is a stabilizer. And finally, because H was a stabilizer, it must be conjugate. It must be a conjugate of GU by some group element G prime, and you just find your G as a conjugate of C by the same group element G prime. But the meaning is that if you know, you might don't know the graph, but if you know the group and you know that one vertex stabilizer for some reason, then you can check if this is really, to the family or not. And we are now ready to give the sketch of the whole proof. So this is our result. The class C contains the following H-transitive graphs of twice odd order. KC, the Peterson graph, the complement of the Peterson graph, and this graph. And of course, we assume that the graph has a valency at least 6. So we assume that the valency is at least 6 because small valencies were considered before. So the valency at least 6, and actually we want to show that no graph exists if it's not the complement of the Peterson. So suppose that still exists, and take the counter example of the smallest order. So the order is larger than 10, and this is the smallest possible. And now by the lemma, we know that we have a non-trivial cyclic block B. You take the cyclic block. Now, because the C has odd order, the block size is surely less than half of the order of C. And because of that, we just observe that C contains a normal subgroup, namely the stabilizer, the server stabilizer of B and C must be normal. And now you take a subgroup of prime order in this normal subgroup. And because it follows that this subgroup P is normal in the full automorphism group, and you can take the quotient with respect to this normal subgroup of order P. The quotient, again by the lemma, the quotient graph must be a quotient graph in the family, which is still H-transitive with respect to this quotient group. By the minimal condition, it follows that N should be 5 times P, and the quotient graph must be the complement of the Peterson, and the quotient group must be A5 of S5. Now, it's possible to find the group structure of your graph gamma. The group structure of the graph gamma is either, there are 3 possible group structures. It is a direct product of ZP with A5, ZP with S5, or a semi-direct product, but the action of S5 on P is well described. It acts, as I say, it fixes an element for the even permutations and inverse element for the odd permutation. The next step is to find a stabilizer. Remember, we want to use the lemma, and it's not difficult to find this small group as the stabilizer. And the final contradiction will arise by just simply applying the lemma 5 to G and H. We don't know the graph, but we know it's automorphism up to 3 cases, and plus we also know the stabilizer. And in that case, the lemma said that the graph should have an element of order n. Now we should have an element of order 5p, satisfying some conditions. And you write this element then z times sigma, when p is a z is a generator of p, and sigma is a 5 cycle. And then it turns out that this condition reduced to a condition in S5. So in that case, this is the reduced condition, but this is a condition of S5. So H is in S5, sigma is in S5. And you want to check this is true in S5 or not, and this turns out it is impossible. In that case, you have some different condition, but still S5. So we reduce the problem without, this is a sub condition which doesn't involve P at all. It's independent of P. And both are impossible, and this is how we show that by contradiction that there is no graph in the class which is twice odd order and larger than the order is larger than 10. Okay, so after this is actually our first result. I also have a second result. I will not explain it with details. I just show you the result. So the second result about the classification of all H-transitive hexavalent graphs in the class C. So this is the graphs which Robert and the co-authors call next graphs. And this extends their result, which deals with the graphs of GERS3. Now we don't need this GERS3 restriction, and these are the families. And actually, I just want to comment that the proof, I follow the same strategy, namely consider cyclic blocks also in this case. And it turns out that the cyclic blocks has size either 1 or 2. And if the cyclic block is 1 or 2, then you have the sporadic examples. Otherwise, the cyclic block is half of the order of the cyclic group. And then you have the families, and this leads to families A and B. And if n is odd, then you don't have this. So it's the n even case is somehow, this shows you this, in some sense is more complicated. To sum up, I just would like to summarize my talk. So all H-transitive graphs in the class C of density atmos 6 are known. We consider the special class of bicirculants, and we just observe that all H-transitive ones of valence atmos 1 are known. In the talk, we actually showed that no such graph exists if the valence is larger than 6, but the order is twice an odd number. And the possible future work is, of course, to extend the method from twice odd order to arbitrary order by conjecture that no graph exists if the valency is larger than 6. And in the end of my talk, I would like to pose 2 questions, which is related but not strictly related. The first question is there a polynomial algorithm for recognizing whether a given graph belongs to the class C? I know some articles when they considered this question in the special case when the graphs are generalized Petersen graphs. There are some results in this field, but now I would like to see it, not all generalized Petersen graphs, but the generalization is for this class C. And the last question is generalization. For the first question, is there a polynomial algorithm for recognizing whether a given graph is a bicirculant? So bicirculant, I just mean that it admits an automorphism 2 orbits of the same size. So it's something like Cayley graph of cyclic group. For Cayley graph of cyclic group, you have 1 orbit, now you have 2 orbits of the same size. And I know that for circulants exists such algorithm. So it's natural to ask, how about the circulants? I would like to show you the references. So the paper with Janos we just submitted, I will put this in the archive. The other result on the classification is still is before submission. And that's it. Thank you for your attention.
Thank you very much for the nice talk, Istvan. Thank you very much. Are there any questions to the speaker?
Yeah.
Yes.
Maybe, yeah, I have one small question. And Istvan, and what do you think? Are such graphs of valency greater than 6 and arbitrary order can exist or not? Maybe do you know some examples of such graphs?
H-transitive.
Yes, yes. H-transitive of valency greater than 6.
I think there is no examples.
Even with small number of vertices.
I don't know any example, and I can show you again this slide with the computational result. So Robert Jajca and the co-authors, they computed H-transitive graphs of valency 7 and 10, and the order is 100.
I see, yeah. I see.
So they computed this in this range, and in this range, no graph appeared.
Yeah, thank you. Yeah.
So no graph is known.
Yeah, I see. Thank you. Thank you. And Maybe do you have some suggestions how it is possible to construct such examples, or do you think that there are no such examples?
My conjecture, no graphs. And this is, we proved it when n is odd. And I would like to carry out the same proof for n even. But n even, there are many difficulties. So one difficulty is this, for example, if n is even, you don't need to worry about these affine group actions, because the degree is 4, 8, 6, and it's not appear for n is odd. So one difficulty is to handle this. This case will appear at some point. The other difficulty is I used the classification of R-transitive circulants, and the reason I can do it is because if n is odd, then you get a Kerr graph over a cyclic group right here. So see, and this involution and C always generates, okay, so you get a graph also in the even case. So you have this cyclic group, you have this involution, and they generate a regular group, which is cyclic because the order of C is odd and the order of T is 2. But in the general, you get a R-transitive Kerr graph, not over a cyclic group, but over a group Z2 times Zn. So we cannot repeat this trick here because we don't have classification of R-transitive graph over such abelian group. It's also an interesting problem because it's, I suppose it's very similar. I suppose the classification is very similar, where you can ask, what are the Schur rings? What are the structure of Schur rings over abelian group Z2 times Zn, right?
Yeah,
so
yeah.
This is the other difficulty, which is you should think about it when you do the even case. But I think it's possible to overcome this. Only more computations and more effort. And my conjecture that in the end, the answer will be that no graphs if the valence is larger than 6.
Thank you so much. Yeah, thank you.
Any other questions?
If I may.
Yeah, sure, please, sure.
I don't really have a question per se, but first of all, I would like to clarify that it's a little unfair. I'm the first author, but I wasn't necessarily the leader of the team. So when Istvan says Robert and the others, it's really, we all worked on this together. And I believe nobody else from our group was watching Istvan today, but we definitely want to see Istvan's proof, and we're looking forward to the proof. I really want to see it and discuss it with Istvan at some point. So I really liked your talk. Thank you very much.
Thank you, Robert, and definitely I will send you the manuscript.
Thank you very much, Robert, for your comments. Let me remind to all participants that Robert will give a talk on new generalization of generalized Peterson graph, which are mentioned in this talk given by Istvan. So this topic will be continued in one day. Okay, are there any other questions to Istvan? Well, if not, then let us say again. Thank you very much. It was really great talk. Yeah, two very interesting open questions. Actually, a lot of questions around of these two open questions, right? Yeah. Yeah. Okay. We are looking forward to have your new results. Thank you very much.
Thank you, Anna.
Thank you.